In this video, we are going to use the principle of mathematical induction to prove that a raised to the 2 to the power of n minus 1 equal a minus 1 times the product of a raised to the 2 to the I plus 1 from I equal to 0 raised to the n minus 1 for every positive integer n. So we have to show that this one, a raised to the 2 to the n minus 1 is a minus 1 times a to the 2 to the 0 plus 1 times a to the 2 to the 1 plus 1 and all the way and so on to the n minus 1 term. So let's get started. So we gotta let Pn. So we let P of n to be a to the 2 to the n minus 1 equal to a minus 1. Oh, let me just write b, okay? B, this one, and is equal to a minus 1 times the product from I equal to 0 to n minus 1 times a to the 2 to the I plus 1. So you get to have the product of this term from I equal to 0 to I equal to n minus 1. So we start from the base step. So what is the base step? We are using the mathematical induction. In the base step, we need to let n to be 1. So we gotta have a to the 2 to the 1 minus 1, which is a to the 2 to the 1, which is a minus 1 times a plus 1. Actually is the difference of square, right? Okay, a square minus b square equal to a minus b times a plus b. And what is this one right here? This term is similar to this term, but for this a is going to be a to the 2 raised to the 0 plus 1, which is a minus 1, and the product from I equal to 0 to 0 and a to the 2 to the I plus 1. Okay, and this 0 actually is 1 minus 1. This is 1 minus 1. Okay, so that means that P of 1 is true. So we have proved the base step. Now what about the inductive step? So what is this step? For this step, we have to assume that. We will assume that P of k is true. Okay, P of k is true for all positive integer k. And we try to show that P of k plus 1 is true. Okay, great. So now this is what we have. So since P of k is true, what do we have? When P of k is true, we gotta have a to the 2k minus 1 equal to a minus 1 times the product of I equal to 0, k minus 1, and a to the 2 to the I plus 1. Okay, and try to write this product. What do we have? We gotta have a minus 1 times a to the 2 to the 0 plus 1, a to the 2 to the 1 plus 1, a to the 2 to the 2 plus 1, and all the way to a to the 2 to the k minus 1 plus 1. Okay, so you're gonna have a minus 1 times a to the 2 to 0 is 1, a to the 2 plus 1, a to the 4 plus 1, and plus all the way to a to the 2 to the k minus 1 plus 1. Okay, great. Then we try to show that p of k plus 1 is true. How can we do? So we start to plug in k plus 1 into this n. So we gonna have this. So we have a to the 2 to the k plus 1 minus 1. And then we're gonna have this. We're going to have a to the k to the a to the 2 raised to the k, and this is 2 to the k plus 1, so we're gonna have number 2 right here, and minus 1. Then we're gonna have a to the 2 raised to the k square minus 1. This is the property of the exponent. Okay, if you have a to the m times and raised to the n, you're gonna have a to the m times n. And then I'm trying to use the difference of square. So we're gonna have a to the 2k square minus 1 times a to the 2 to the k plus 1. Okay, great. Then what do we have next? So we have this term right here, which is this. So we plug in this term, which is from the fact that p of k is true. So we will substitute this term into here. So we gonna have a minus 1 times a plus 1 times a to the 2 plus 1 times a to the 4 plus 1 and plus all the way to a to the 2 to the k minus 1 minus 1 and a to the 2 to the k minus 1 times a to the 2 to the k plus 1. Oh, I forget that it must be plus. Okay, plus right here and plus right here. Then what do we have next? So we can have the product of a right here, a to the 2, a to the 4, and a to the k. Okay. Okay, give me a second. For this term become this one, right? Oh, I just write this term twice. Sorry. So we gotta have just this. Okay, because this term right here is just a. You gotta have a raised to the 2 to the k minus 1, which is the last term right here. So we gotta have this big bracket right here. Now, what do we have next? We gotta have a minus 1 big bracket, and this term is a plus 1, right? And a plus 1 becomes a to the 2 to the 0 plus 1 times a to the 2 to the 1 plus 1 times a to the 2 to the 2 plus 1 and plus all the way to a to the 2 to the k minus 1 plus 1, and this one too. We gotta have a to the 2 to the k plus 1. That's it. And then we can write this product as in notation of big pi right here. So we're gonna have a minus 1 big pi from I equal to 0 to the k. Okay, to the k, which is a to the 2 to the I plus 1. It's actually become a minus 1. Start from I equal to 0. The product of a to the 2 to the I plus 1. And we're gonna have a plus 1 minus 1 right here. Okay, and we have shown that p of k plus 1 is true. Okay, so we have proved that the inductive statement is true, so we have shown that. Therefore, so we have shown that if you have a raised to the 2 to the n minus 1, we gotta have a minus 1 times the product from a equal to 0 to n minus 1 times a to the 2 to the I plus 1 for every positive integer n. Okay, so we already proved this statement, and that's it for this video.